Hi, everybody. Here to discuss the last thing about infinite sequences. It's the bounded monotone sequence convergence theorem, and maybe an application or two of it. So, if you have a sequence that is increasing, and by that I mean each term is at least as big as the previous. So like here's an A1, and then here's an A2 on the number line a little beyond it, and an A3 beyond that, and an A4. And just keeps on going like that. That's an increasing sequence. But suppose that there's an upper bound. Suppose that for some m, all the ANs are less than or equal to m. Like maybe this number here, serving as an upper bound. Then what has to happen to the sequence? It turns out, there's a theorem, that the limit as n goes to infinity of an exists. And that limit has to be less than or equal to m. You can kind of intuitively tell why the theorem would have to be true, because if the ANs have to keep going up, but they cannot go past the m, they've got to crowd somewhere. Like here, they're crowding at this number L, the limit. That L could be less than m, but it cannot be bigger than m, because if something bigger than m were the limit, there'd have to be some a's that were past the m to be getting towards the L. On the other hand, suppose that your sequence is decreasing and all of its terms are bigger than some lower bound m. Then also the limit of an will exist, and it'll be bigger than or equal to m. Those two statements together are known as the bounded monotone sequences converge theorem. It's a theorem that's proved in more advanced mathematics. Even though it's intuitively true here, it's not something we have the machinery to actually prove. So with that in mind, let me take a look at a recursively defined sequence. And let's see if this is like an easy sequence or a hard sequence to think about the limit of. I'm going to let a1 be the square root of 2. And then for n bigger than 1, my builder rule is that an shall be the square root of an minus 1. And I'm wondering, does the limit of an exist as n goes to infinity? And if so, what is it? Well, when I think about it, I write out a few terms. That's my a1. And then my builder rule says that the a2 would have to be the square root of the a1, so square root of 2. And then my builder rule says that the a3 has to be the square root of the a2, so square root of the square root of the square root of 2. And when I look at this, it's like powers of powers of powers. This is 2 to the 1/2. But then this square root I've got thrown on here is taking my 2 to the 1/2 and raising it to another, 1/2. And that's 2 to the 1/2 times 1/2, which is 2 to the 4th. And then here we've got a 2 to the 1/2, 2 to the 1/2, 2 to the 1/2. That's 2 to the 1/2 cubed. It's 2 to the 1/8. In general, we got a formula. We've got a formula for the general term. We don't need the builder rule. We've figured out that for any n, an is 2 to the 1 over 2 to the n. And that makes it a lot easier to think about the limit of an. We can just think about the limit of that general term expression. And what we've got here is a continuous function, exponentiation with base of 2. The limit of that exponentiation function applied to the sequence 1 over 2 to the n. So that's 2 to the limit of 1 over 2 to the n. That's 2 to the 0, that's 1. That was not hard to do. But tweak the problem just a little bit and you can make it a lot harder to think about. Let's let a1 be root 2, and this time for n bigger than 1, let's let our builder rule be an is square root of twice an. So now we're looking at square root of 2, square root of twice square root of 2, square root of twice what we had before, and so on. And I don't really see a nice way to make just a general term, an equals some expression involving n, out of this. So maybe think about it another way. I'm going to make two useful observations about that sequence AN. First of all, it's bounded above. Why do I say that? Well, I would like you to notice that A1, which is square root of 2 by definition, is less than 2, because square root of 2 is about 1.4. That's less than 2. I would now like to have you look at A2, which by the builder rule is square root of twice A1. Okay? Now, A1 is less than 2. So if I just replace the A1 with a 2, getting this, I have something bigger. So A2 is less than the square root of 2 times 2, which is the square root of 4, which is 2. So I have just found that A2 also has to be less than 2. How about A3? Well, that's the square root of twice A2 according to the builder rule. And I just found A2 was less than 2. And so square root of 2A2 would be less than square root of 2 times 2, which is 2. Now I've shown that A3 is less than 2. Hey, I could keep doing that. Continuing in that way, for any n, I could show that an is less than 2 by using that an minus 1 is less than 2. So what I've got is a bounded sequence. It's bounded above by 2. Okay? Now, another useful observation to make about the sequence an is that it is increasing. And why do I say that? Well, look at a sub n plus 1. By the builder rule, it's this. But I know that 2 is bigger than a sub n. The sequences are bounded above by 2. So if I replace the 2 with an an right here, I will have something smaller. And that something smaller is an. So I've just shown that an plus 1 is always going to be bigger than an. So my sequence does increase. So looking up at my theorem 6, I'm in this situation where I'm looking at an increasing sequence that is bounded above by a number. Therefore, that sequence has to have a limit. Okay? That's nice to know. But there's more. So it's got to have this limit. I'm going to call it L. And I know it's got to be a positive number because the A1 is already square root of 2, and then it's an increasing sequence. Everything's positive. I'd like to actually see if I could find what that number L is. So to that end, I'll have you consider the builder rule again. And what if we took the limit as n goes to infinity of both sides, like this? Now on the left, you're looking at the limit of the sequence A2, A3, A4, A5. You're starting with A2 because you're looking at an plus 1. It's the same sequence as A1, A2, A3. It just starts one place later. So it's got to be going to the same place that the regular sequence is going to. Doesn't matter where you start when you're looking for what the limit is. You'll go to the same limit. So that limit here is going to be an L. Now on the other side, I'm looking at this limit, which I can write as the limit of square root of 2 times square root of an. And I can bring the constant outside. And so I've got this situation now. And square rooting is a continuous function. I can put the limit sign inside the continuous function. The limit of continuous function of an is the continuous function of the limit of the an. So now I've got this situation. But the limit of an is L. So I've got an equation here. I can solve it for L. I can divide both sides by the square root of L because L is not 0, and so the square root is not 0. And I'll get this. And on the left, that simplifies to the square root of L. So I've got square root of L is square root of 2, so L must be 2. So the sequence was bounded above by 2, and actually it creeps up closer and closer to 2. That's its actual limit. So that's something that was really hard to find by any techniques that we've learned previously, but the theorem 6 that allows us to conclude that it has a limit, that was really useful, because then we could use that fact together with the builder rule to set up an equation to solve for the unknown limit. Really nice. One last bit of practice before we go. It's nice to be able to just look at the first few terms of a sequence and come up with a suggestion for a general term for the sequence. So like, what if these were your first few terms? What would be a reasonable suggestion as to what the general term is? Well, I notice it cycles between positive and negative numbers. And I notice I get bigger numbers on the bottom, and those numbers look like cubes, like a 2 cubed and a 3 cubed and a 4 cubed. And you know what? I could imagine a 1 in the bottom of a fraction there, and I could think of the 1 as a 1 cubed. So that gives me the idea of using like an n cubed for my general term on the bottom. Now I need to cycle, though, from 1 to minus 1. So I'm not going to be able to use a minus 1 to the n, because if I start with n equals 1, minus 1 to the n is just a minus 1. I need a 1 there. So try minus 1 to the n plus 1. Then when n is 1, I got minus 1 squared. I've got my 1. When n is 2, I'll have my minus 1 cubed, and I'll catch that negative 1 like I need. So that would be a reasonable suggestion for maybe what the whole sequence is. Could we find a reasonable suggestion about the general term for that sequence, given just these few first terms? I might just do n over n plus 4, noticing that the denominator is always 4 bigger than the numerator. I'll need to start at n equals 2, though. I could just as well do n plus 1 over n plus 5, and that way I could start with n as 1. Again, when you're writing down a sequence, it doesn't matter, where you choose to start for your domain. But once you've made a choice for your domain, that affects what a good formula for the general term will be. That's all I've got for sequences. See you later for another topic.